Imagine you just walk into your kitchen,
Right.
you turn on your tap, and you instantly get a glass of fresh, clean water.
It's just something we completely take for granted.
Exactly. But, okay, I want you to imagine trying to deliver 1,000,000 gallons of water to a city of 1,000,000 people.
Yeah.
And you have to move it like 50 miles across mountains and deep valleys and these just unforgiving swamps.
Yeah, good luck with that.
Right. And here's the catch. You have no electricity, no diesel motors, you don't have pressurized steam engines, you don't have a single mechanical pump. How do you do it?
It sounds completely impossible.
It really does. But today we are taking a deep dive into the terrifying, just mathematically flawless, gravity-powered engine of the Roman aqueducts.
Oh, man. The sheer audacity of these structures is just, it's mind-blowing.
It really is. We're pulling from this incredible stack of research today, historical engineering texts, modern archaeological surveys. And our mission for this deep dive is to really just unpack the wildly complex physics of moving an ocean of water across vast distances using absolutely nothing but the raw, silent pull of gravity.
Yeah, and to really grasp the magnitude of what the Romans achieved here, we have to kind of strip away all our modern comforts. We need to establish the baseline reality of the ancient Mediterranean world.
Right, because before aqueducts, survival was pretty precarious, wasn't it?
Totally. You relied entirely on highly localized, really vulnerable water sources.
Yeah.
If you were a citizen of early Rome or, any developing ancient city, your daily routine revolved around natural springs or maybe muddy little streams.
They're just privately owned wells dug deep into the dirt.
Exactly. And there was this massive reliance on simple rainwater catchment, like literally just leaving large clay jars out or using rooftop cisterns to collect runoff.
Which, I mean, that's perfectly fine if you're living in an isolated farming village, right? You get a little rain, you pull some water from the well, you survive.
Sure, for a village, it's fine.
But if you're trying to build a metropolis, that local catchment area basically acts as a hard physical ceiling on your population, doesn't it?
It creates an absolute bottleneck for growth. You can only sustain the number of people that your local aquifer can actually support.
Yeah.
And Rome was growing at this just unprecedented rate.
Right, going from a regional power to a massive urban center.
Yeah. And, well, the obvious geographical feature of Rome is the Tiber River. The city is built right on its banks.
So why not just use the river?
Well, by the time Rome was expanding rapidly in the 4th century BC, the Tiber was essentially a massive open sewer.
Oh, gross.
Yeah, it was heavily polluted by agricultural runoff, butchery waste, waterborne diseases.
Yeah.
You couldn't just dip a bucket in the Tiber and hand it to a child to drink.
Right, you'd get sick immediately.
Exactly. So to grow, Rome desperately needed external, uncontaminated water.
They needed like an entirely new river flowing through the air directly into the city.
That's a great way to put it. And this need really forces their hand in the year 312 BC. Rome is right in the middle of the Third Samnite War.
Which was this brutal existential conflict for control of the Italian peninsula, right?
Yes, exactly. And right in the thick of this war, they commission their very first aqueduct, the Aqua Appia.
And the context of that war dictates the entire engineering strategy of the Aqua Appia, doesn't it?
It really does. Because the city is under constant threat, this first aqueduct is built almost entirely underground.
Oh, wow. So it wasn't those big arches we always picture.
Not at first, no. It was a strategic security measure. I mean, if you have a highly visible, elevated water channel marching across the countryside, an invading army can just, well, they can simply smash a section with sledgehammers.
Or, worse, toss animal carcasses into the water supply.
Exactly. Biological warfare, essentially. So the Aqua Appia was a military asset just as much as it was a public utility. It tapped a spring a little over 16 kilometers outside the city walls.
Okay.
And over that entire 16-kilometer subterranean journey, it dropped a total of just 10 meters.
Okay, let's unpack this. 10 meters of drop over 16 kilometers.
Mm-hmm.
How do you actually pull off an engineering miracle of that scale in 312 BC?
It's tough to wrap your head around.
I mean, you have no motors to push the water. You are relying entirely on the Earth's natural contours to do the heavy lifting.
Right. The invisible engine driving this entire civilization is just the math and physics of the downward gradient.
So it's all about the slope.
Yes. The fundamental, unbreakable rule of any Roman aqueduct is that it must feature a slight, continuous, overall downward slope from the source spring to the city terminal. Gravity does 100% of the work.
Wow.
But, you know, the true genius of Roman engineering isn't just making water flow down a hill. I mean, anybody can dig a ditch down a hill.
Right,
The
shallow.
genius is making it flow down the hill at exactly the right speed.
Because if it goes too fast, the friction and the weight of the water basically turn it into a weapon against its own channel, right?
An absolute catastrophe. To understand the danger, we really have to look at the recommendations of the famous Roman architect and engineer Vitruvius.
Right, he wrote extensively in the 1st century BC.
Exactly. He recommended that an aqueduct should have a gradient of not less than 1 in 4,800.
Okay, wait. Let me do this.
Yeah, so that means for every 4,800 feet you travel forward, you drop only 1 foot.
That's insane. It is an incredibly, almost imperceptibly flat slope.
It is.
But why so flat? Like, if I'm building a water slide, I want a steep drop. I want it to go fast.
Well, it comes down to the destructive physics of kinetic energy. Water is incredibly heavy. A single cubic meter of water weighs a metric ton.
Oh, wow.
Yeah, so if you build your channel down a steep hill, gravity accelerates that mass. As the water speeds up, it gains immense abrasive force.
So it acts like a giant liquid grinding wheel.
Exactly that. It would scour the stone floor, erode the specialized waterproof mortar, rip out the brickwork at the joints. I mean, it would ultimately destroy the very structural integrity of the conduit meant to contain it.
I am really trying to wrap my head around the level of precision required to maintain a slope that shallow over wild terrain.
It's staggering.
Like in our source material, the breakdown of the Pont du Gard aqueduct in modern-day southern France is just unbelievable. This structure spanned 50 kilometers from the natural spring to the city of Nimes.
Yep.
But over that entire 50-kilometer journey, winding through the countryside, the channel drops a total of only 17 meters vertically.
Yeah, that translates to a gradient of just 34 centimeters per kilometer, or to put it another way, about an inch of drop for every football field of length.
Think about that. It is like trying to roll a heavy steel marble down a 50-kilometer track.
That's a good way to picture it.
And over that entire distance, the track only drops the height of a 2-story house. You have to engineer this track so flawlessly that the marble never ever stops rolling and pulls up, but it also never gathers enough speed to fly off the rails.
That's a brilliant way to visualize the tension the engineers faced. I mean, the Pont du Gard was transporting up to 20,000 cubic meters of water daily on that minuscule slope.
So they messed up even a little bit.
Exactly. If the surveyors miscalculated and made a section perfectly flat, the water stalls. It pools, the pressure backs up behind it, and it eventually breaches the walls of the channel.
And if they made it too steep?
If they made it just a fraction of a degree too steep, the continuous friction of thousands of tons of fast-moving water would tear the channel apart from the inside over the span of just a few years.
But nature isn't perfectly smooth. You can't just draw a gentle sloping line on a map and expect the Earth to cooperate.
No, definitely not.
So what happens when they were building this channel, maintaining that perfect 34-centimeter drop, and suddenly the ground plunges down a massive steep hill? They can't just slope the pipe down the hill.
Right, the marble would turn into a cannonball.
Exactly.
Well, this is where their mastery of applied hydraulics really comes into play. When the terrain forced them to lose elevation quickly, they didn't just angle the conduit downward. They built step cascades, vertical drop shafts, and heavily reinforced receiving tanks.
Okay, so like a staircase.
Yeah, imagine a massive internal staircase for the water. The water flows horizontally to the edge, then pours into a vertical shaft. It drops straight down into a plunge pool or a holding tank at the bottom.
Oh, I see.
And the impact of hitting that pool instantly kills the water's forward momentum. It dissipates all the dangerous kinetic energy. Then the water gently spills over the lip of the pool and continues into the next horizontal channel at the new lower elevation.
That's so smart. They essentially built ancient speed bumps. They're forcing millions of gallons of water to hit a wall, calm down, and resume walking speed.
Yes, and what's fascinating here is there was a completely unintended yet highly beneficial side effect of these drops.
Really? What was that?
Well, when water falls and violently splashes in these cascade shafts, it churns up heavily. This aerates the water, folding oxygen back into the flow.
Oh, wow.
Yeah. In a system where water might be spending days creeping through dark, sealed underground tunnels, these drop shafts essentially acted as natural purifiers. They kept the water highly oxygenated and fresh tasting by the time it reached the city.
That is a brilliant architectural accident.
Yeah.
But it raises a massive logical question for me.
Okay, what's that?
If the flow of this water and avoiding stagnation in those incredibly flat sections depends entirely on having a constant heavy volume of water pushing from behind, how do you guarantee the volume?
Ah, yeah.
Like the Romans couldn't control the weather. If there's a harsh drought, the water volume at the spring drops, the flow weakens, and doesn't the water just sit in those flat tunnels and fester?
You've hit on the most critical vulnerability of the entire gravity-fed paradigm. They were entirely at the mercy of the catchment hydrology.
Because they can't make it rain.
Right. They couldn't control rainfall, and they couldn't control how much water the Earth absorbed versus how much it released. This is exactly why the initial surveying of the water source was an obsessive, almost religious process.
So they didn't just pick the first creek they found.
Definitely not. They didn't just find a random puddle or a seasonal creek and start building a 50-kilometer monument. They searched for deep-seated, high-yield aquifers and perennial springs that flowed year-round, regardless of drought.
But wait, how do you even find a deep aquifer without modern ground-penetrating radar?
Well, Vitruvius actually wrote a veritable manual on water prospecting. The engineers would study the surrounding vegetation, looking for specific plants that only thrive with deep, constant moisture.
Like tracking the local botany? That's clever.
It gets crazier. They would literally lie face down on the ground before sunrise, resting their chins on the dirt, looking for faint morning mists rising from the soil, which indicated subterranean water.
You're joking, just staring at the dirt at dawn.
Literally just staring across the dirt. And when they finally located a reliable spring, they didn't just stick a pipe in the mud. They built a caput aquae, a formal stone or concrete spring house.
What was that?
This acted as a gathering basin to protect the source and regulate the initial flow into the conduit. And if one spring wasn't generating enough volume to maintain that critical mass, they would build a complex network of feeder branches.
Oh, like a river system in reverse.
Exactly, like the roots of a giant tree. They'd gather multiple scattered springs across a valley into one main torrential channel to ensure the flow never weakened.
It is a relentless, exhausting battle against geography and physics.
Oh.
Okay, so they know the math. They know they need an imperceptible drop. They've found a massive spring.
Right.
Now they have to physically map a route across completely chaotic natural terrain, through forests, across swamps, around mountains,
Right.
and they have to maintain that flawless slope in the dirt. How do you do that without lasers, without GPS, without modern optical theodolites?
You do it with an almost incomprehensible amount of patience, staggering human labor, and a suite of very clever, purely analog tools.
Okay, I'm ready. What tools?
The Roman surveyors, a highly respected profession known as the Libratores, had to measure horizontal levels with excruciating accuracy over miles of rugged wilderness. Their primary tool for this was a device called a Chorobates.
Okay, yeah. I saw diagrams of the Chorobates in the research, and I have to be honest, it looks incredibly rudimentary. It looks like a long wooden bench.
I mean, it is essentially a flat-bedded wooden bench, usually about 20 feet long, with legs at either end.
And how does a bench measure a slope?
Well, to check if the ground beneath it was perfectly level, the surveyors hung plumb lines, strings with heavy brass or lead weights on the ends from the sides of the frame.
Okay.
If the strings hung down and aligned perfectly with specific notch marks carved into the wooden legs, you knew the bench was sitting perfectly horizontal.
Wait, if they are out in the field, hacking their way through a valley in Gaul, what if it's windy? A plumb line is just a string. A stiff breeze is going to send those weights swinging violently.
Oh, for sure.
You can't base a 50-kilometer engineering project on a swinging piece of string.
And the Libratores anticipated that exact problem. The Chorobates featured a secondary leveling mechanism. Down the center of the 20-foot wooden top, they carved a long, shallow groove.
Okay.
On windy days, when the plumb lines were useless, they would pour water into this groove. Because water is subject to gravity, its surface will naturally always find a perfect horizontal level.
Oh, that is so simple, but so brilliant.
Right. So, by getting down at eye level and looking at the water line against the meticulously carved edges of the groove, they could establish a flawless horizontal plane, even in a gale.
But the bench is straight. They need a slope.
Right. Once they established true horizontal using the water groove, they could calculate the minute angle of descent required for the next segment of the trench, using small wedges or calibrated markings.
Oh, okay.
They also employed a tool called a groma, which was a vertical staff planted in the ground with a horizontal crosspiece on top and 4 plumb lines hanging from the arms.
And what was that for?
The groma was used to plot perfectly straight lines across the landscape and to establish exact right angles. And then later in the empire's history, they adopted a sophisticated Greek instrument called a dioptra.
Which was more advanced?
Much more. This was a complex, tripod-mounted setup utilizing interlocking gears, water levels, and sighting tubes. It allowed them to calculate angles and distances using early trigonometry.
I'm still struggling to accept this. You're telling me a team of guys carried a 20-foot piece of wood into a swamp, poured a puddle of water into it, squinted at the water line, and used that to map a route that drops exactly 34 centimeters over a kilometer.
Yep, pretty much.
But what if the wood warped in the rain? What if the surveyor's eyesight was slightly off? An error of a fraction of an inch on that bench, compounded over 50 kilometers, means the aqueduct emerges underground or stops flowing entirely. It just seems mathematically impossible that analog tools alone were sufficient.
Your skepticism is completely warranted, and you've actually identified the great myth of Roman engineering.
Really? What's the myth?
The tools alone did not guarantee success. What made these aqueducts function was the staggering brute force application of trial, error, and limitless labor.
Okay, so they messed up a lot.
Constantly. They didn't just walk the route once with the Chorobates, plant some flags, and start laying concrete. The Libratores surveyed the line, then they dug extensive test trenches.
Like practice trenches.
Exactly. They would literally dig a mile of trench, let water flow into it, and watch what happened. If the water pooled or if it ran too fast, they realized their bench reading was wrong.
Oh, wow. So what do?
They would have to rip out the trench, adjust the slope, and dig it again. Building an aqueduct wasn't a project measured in months. It was a grueling campaign measured in decades.
Decades.
Yeah. And because this mathematical slope was so delicate, the Roman state had to construct a rigid legal framework just to protect the physics of the trench.
Yes. The clear corridor laws. This fascinated me in the source material. They couldn't just build the aqueduct. They had to legally quarantine the land around it so nobody could mess up the math.
Precisely, because the conduit is so physically sensitive to external pressure and vibration. The Senate passed strict laws establishing a protected, empty corridor along the entire length of the aqueduct.
How wide was the corridor?
Typically, this was 15 feet of cleared space on either side of the channel in rural countryside areas and 5 feet in highly congested, built-up city zones. They physically marked these quarantine boundaries with large, inscribed stone slabs called cippi.
And the rules inside that corridor were absolute, right? No new dirt roads crossing over the buried conduit, no new buildings constructed near it.
No agricultural plowing that could destabilize the soil, and above all else, absolutely no trees.
Why trees? That seems so specific.
Trees were considered a primary threat to the empire's infrastructure. The roots of a tree are relentless in their search for moisture. If a tree grows near an aqueduct, the roots will sense the microscopic condensation or slight seepage from the masonry.
And they just go right for it?
They go right for it. They will grow directly toward the stone, wrap around the channel, crush the exterior mortar, and physically wedge themselves between the bricks, penetrating the conduit.
That's terrifying, just slow-motion destruction.
It is. This causes massive leaks, destabilizes the gradient, and leads to structural failure. Frontinus, a Roman general who later served as the curator aquarum, the supreme water commissioner, explicitly documented that tree roots were one of the most destructive and frustrating forces his maintenance crews faced.
It's incredible to think that keeping a city alive meant fighting physics, biology, and, as I read in the sources, property law.
Oh, the property law was the worst part.
The legal battles to secure the land for these 50-kilometer corridors sounded like an absolute nightmare of red tape.
The legal and political landscape was often more treacherous than the physical terrain. Roman planners, of course, preferred to build the aqueduct across Eger Publicus, state-owned public land.
Because it's free.
Exactly. It was legally simple and cost the treasury nothing, but water doesn't care about property lines. To maintain that perfect economical gravity gradient, the route inevitably had to carve straight through privately owned farms and sprawling aristocratic estates.
And I'm guessing rich Romans didn't like giving up their land.
Oh, wealthy Roman landowners were fiercely protective of their property rights. Sometimes the state would use eminent domain to buy an entire estate, carve out the aqueduct corridor, and then try to resell the leftover parcels.
But what if they just said no?
If a powerful landowner flatly refused to sell, you were looking at rancorous, interminable court cases that could stall construction for years.
The text highlighted a specific incident with M. Licinius Crassus, a wildly wealthy landowner around 179 BC. The state censors are trying to map out a massive new aqueduct, and the mathematically perfect route goes right through his fields. Crassus simply says no. He refuses to grant right-of-way.
Yep.
And he actually forces the complete abandonment of the entire infrastructure project. A single, stubborn, rich guy stopped a vital public utility for the capital of the known world.
It perfectly illustrates that Roman engineers didn't operate in an academic vacuum. They were heavily constrained by politics, aristocratic pride, and even religion.
Religion. How does religion stop an aqueduct?
Look at the Aqua Appia, commissioned in the 140s BC. This was intended to be a magnificent structure supplying the high elevation of the Capitoline Hill, but the project was completely legally paralyzed for years on religious grounds.
Wait, really?
Yeah, a conservative political faction consulted the Sibylline books, Rome's most sacred written oracles, and magically claimed to find an ancient prophecy warning against bringing piped water to the Capitoline.
Oh, so they weaponized the religion to stop the build.
Exactly. It brought the entire massive engineering project to a dead halt until the Senate finally gathered the political willpower to force it through. When we marvel at the physical stonework of an aqueduct, we must equally respect the brutal political engineering required to even break ground.
So eventually, the politicians win, the land is secured, and the surveyors with their chorobates march forward. But eventually, they are going to hit a piece of geography that they cannot legally or physically go around.
It's inevitable.
They hit a solid mountain range, or the ground falls away into a massive plunging river valley. How do they conquer the landscape when the delicate gradient meets an impassable obstacle?
Well, if the surveyors hit an obstructing mountain peak, the default preference was always to circumvent it. They would try to follow the natural contour lines, wrapping the aqueduct around the base of the mountain.
But that adds distance, right?
Exactly. If that detour added too many miles, ruining the slope or bankrupting the project, they had only one terrifying option. They tunneled straight through the solid heart of the mountain.
I cannot even fathom the claustrophobia and danger of hand-chiseling a tunnel through solid rock in the ancient world. They didn't have dynamite.
No dynamite. It was harrowing, incredibly slow work, often carried out by enslaved laborers. To penetrate solid stone, they utilized a technique called fire setting.
Fire setting. How does that work?
They would build massive, intense timber fires directly against the subterranean rock face. Once the stone was superheated, they would dash freezing cold water, or sometimes vinegar, onto the rock.
Oh, and the temperature change shatters it.
Precisely. The rapid, violent change in temperature caused the stone to thermally shock and naturally fracture. Then, laborers would move in with iron picks and chisels to hack away the shattered rock face, inch by agonizing inch.
That sounds like actual hell.
It was. The Aqua Augusta, down in the Campania region, required an unbelievable 6-kilometer tunnel driven through a mountain simply to switch the water flow from a northerly watershed into a southerly one.
6 kilometers.
6 kilometers of hand-hewn, suffocating tunnel, while still flawlessly maintaining that 34-centimeter drop.
A mountain is a nightmare, but at least it's solid ground. A valley seems infinitely worse. Because when the ground drops away beneath your target slope, you can't dig a trench through empty air. You have to physically support the water in the sky.
And this necessity gives birth to the most iconic, enduring image of the Roman aqueduct, the arcade.
Right, the giant arches.
These are the majestic, multiple-piered arches constructed of ashlar masonry, fired brick, or concrete, stepping proudly across a valley. Let's return to the Pont du Gard. When the channel met the wide, deep gorge of the Garden River, the engineers built a massive 3-tiered arcade of limestone.
Just to keep the slope going.
Exactly. It literally lifts the water channel nearly 49 meters over 160 feet above the riverbed, bridging the gap so the gradient can continue uninterrupted on the other side.
It's beautiful, but the sheer volume of stone, the scaffolding, the manual labor required to build a 160-foot stone bridge is astronomical. What happens when a valley is simply too deep or a canyon is too wide for an arcade? Even the Romans couldn't build a massive stone bridge 500 feet tall.
When an arcade became physically impossible or economically unviable, the engineers deployed the absolute technical centerpiece of Roman hydraulic engineering, the inverted siphon.
Ooh, okay. The inverted siphon.
When they couldn't build a bridge high enough, they stopped relying on a gentle slope, and they turned the water itself into a pressurized kinetic weapon.
Wait, I realized something when I was reading the breakdown of how the inverted siphon works. It is exactly the mechanics of a modern roller coaster.
A roller coaster? How so?
Think about it. You are in a roller coaster cart. creeping to the top of a massive hill. The cart tips over the edge, and you drop completely down into a steep valley. That massive vertical drop builds up immense kinetic energy and forward momentum.
Okay, I follow.
You hit the bottom of the track, and that stored momentum shoots you violently back up the steep hill on the exact opposite side, just barely cresting the top. Now, imagine that instead of a metal cart holding teenagers, it is millions of gallons of raw water.
Yes.
And instead of an open track, the water is entirely enclosed in a sealed lead pipe, absolutely screaming under the built-up pressure.
Not only is that a fantastic analogy, but it also perfectly isolates the danger of the mechanism. You are describing a liquid roller coaster operating under terrifying hydrostatic pressure.
So how did they actually build it?
Here is the precise mechanical breakdown of the inverted siphon. The gentle, gravity-fed water channel arrives at the edge of the deep canyon. The open channel flows into a heavily reinforced, specialized reservoir called a header tank.
Right.
From this tank, the water plunges directly down the steep, downward slope of the valley wall. But it's no longer in an open channel. It is now completely sealed inside tight, soldered pipes, usually made of heavy sheet lead, though occasionally hollowed stone or ceramic.
So as that water drops down the canyon wall, the weight of the water behind it is building up immense crushing pressure inside the pipe.
Terrifying pressure. The water reaches the absolute bottom of the valley floor. Instead of just laying the pipes haphazardly in the mud or the riverbed, the Romans constructed a low, flat, very solid bridge across the valley floor.
What did they call that bridge?
They called this bridge the venter, or in Greek, the koilia, which translates literally to the belly.
The belly. I like that.
The high-pressure water races across this flat belly bridge, and then, relying entirely on the immense pressure head generated by that initial vertical drop, the water is violently forced back up the steep slope on the far side of the canyon.
Just blasting uphill.
It blasts upward, fighting gravity, until it empties into a receiving tank that is positioned at a slightly lower elevation than the original header tank on the other side.
So because the receiving tank is slightly lower, the overall macro gradient of the aqueduct is maintained, even though the water just took a terrifying high-speed detour down a canyon and back up again.
Exactly. It is incredibly elegant.
But the pressure at the bottom of that belly must have been astronomical. I mean, the sheer weight of a 200-foot column of water pressing down on a lead pipe.
It was, without question, the single most dangerous explosive point in the entire aqueduct system. Vitruvius, normally very clinical in his writing, wrote almost frantic warnings about the inverted siphon.
What was he worried about?
He warned about sudden blockages. He warned about the pipe joints literally blowing out, bursting violently at the soldered seams, because the sheer hydrostatic force of the water column pushing down was trying to rip lead apart.
How did they stop the pipes from turning into shrapnel? Lead isn't exactly high-tensile steel. It's soft.
They mitigated the pressure using a few brilliant engineering techniques. First, they never ran one massive giant pipe down the hill. That would concentrate too much pressure on a single seam.
Oh, they split it up.
Yes. Instead, they divided the water from the header tank into a manifold of many smaller pipes to distribute the load. For example, in the Aqueduct of the Gers in modern-day France, the siphon had to cross a wide and navigable river.
Wow.
To clear the river traffic, they ramped up the Venter Bridge and ran 9 separate parallel lead pipes side by side across the belly.
So 9 smaller pipes instead of one huge one.
Right. And second, to prevent the lead from ballooning and bursting under pressure, they often encased these parallel lead pipes in thick, solid concrete.
Just burying it in concrete.
Or they carved massive, heavy stone sleeves to fit perfectly around the joints, literally clamping the soft lead together with hundreds of pounds of rock to hold the explosive pressure inside.
Okay, but what about the air?
The air.
Yeah, if you trap atmospheric air in a sealed pipe, and then you send millions of gallons of water rushing in at high pressure, the water doesn't compress, but the air does. Doesn't the compressed air act like a bomb?
Ah, you've identified the phenomenon known in fluid dynamics as a water hammer.
Water hammer.
It is an incredibly destructive force. Gases, like air, are compressible. Liquids, like water, are generally not. If a massive slug of high-velocity water traps a pocket of air in the belly of the siphon, the water rapidly compresses the air.
And the air fights back.
Violently. The air pushes back, acting like a compressed coil spring. It rebounds, sending a supersonic shockwave back through the water column. This shockwave hits the rigid lead pipe and shatters it instantly.
Did the Romans know about this?
Vitruvius deeply understood this danger. He details the critical need to install vertical standpipes, essentially pressure relief valves along the venter bridge at the bottom.
Oh, so the air can escape.
These vertical pipes allowed the violently compressed air to safely vent out into the atmosphere, neutralizing the shock wave before it could blow the system apart.
Okay, let's unpack this. They fully possess the technology to build these complex, high-pressure siphon systems. They could enclose water, clamp it in concrete manifolds, vent the shock waves, and shoot water seamlessly across canyons.
Yeah, absolutely could.
If they could do all of this, why on earth did they spend decades and fortunes of state treasury building giant, massive stone arcades? Why not just use lead siphons everywhere? It seems so much faster to just unroll a lead pipe down a hill and back up, rather than quarrying 1,000,000 tons of limestone.
It is the ultimate question of resource management, and the answer comes down to the severe limitations of ancient material science and the terrifying perpetual risk of storing energy.
So it was just too risky.
Yes, lead was available, but it was incredibly heavy, expensive, and difficult to solder seamlessly over miles of continuous terrain. But the core philosophy is this. An inverted siphon is an active pressure bomb waiting to go off. It is constantly stressed.
Right.
If a mortar joint fails on a traditional stone arcade, what happens? Water leaks out, drips into the valley, and a stonemason patches it the next day. The system survives.
But if a siphon fails...
If a soldered joint fails at the bottom of a high-pressure siphon belly, it explodes violently. It rips up the concrete casing, destroys the adjacent parallel pipes, causes a massive washout of the valley floor, and completely cuts off the water supply to the city for months, while engineers desperately try to rebuild a high-pressure system in a flooded canyon.
That's a disaster.
The stone arcades, though painfully slow to build, were fundamentally passive. They relied purely on the gentle, unstressed carriage of gravity. In Roman civic engineering, passive, massive durability almost always won over high-risk efficiency.
I love that concept, passive durability. You don't want a pressurized time bomb baked into the public utility grid of your empire.
Exactly.
Okay, so whether the water is coasting over a towering stone arcade or gliding through a mountain tunnel, let's talk about the physical conduit itself, the actual tube where the water is traveling. I want to zoom in on the internal environment of this system. If I was standing inside the channel, what does it actually look like?
The majority of the conduits, especially the long, buried underground sections, adhered to a very specific, standardized architectural shape. They were flat-bottom channels with an arched, vaulted roof.
How big were they?
Internally, they were surprisingly compact. A typical conduit was roughly 0.7 meters wide by 1.5 meters high. That's about 2.5 feet wide and about 5 feet from the floor to the peak of the arch.
So an average adult could fit inside, but you would be severely hunched over.
Exactly. These channels were usually buried 0.5 meter to a full meter below the surface of the soil.
To protect it from the weather.
Yes, this burial protected the masonry from extreme temperature fluctuations, prevented the water from freezing in winter or boiling in summer, and protected the conduit from surface vibrations.
What were the walls made of?
The structural shell was built using ashlar masonry in the early Republic, which are large, finely cut square stones stacked without mortar. Later, during the Imperial era, they shifted to brick-faced concrete, which was faster to build and incredibly strong.
Okay.
But the absolute most crucial element of the conduit was the interior lining. The inside of the channel was coated in a highly specialized waterproof mortar called opus signinum, made by mixing crushed terracotta tiles into the lime cement.
Crushed tiles.
Yeah. Once applied, they polished this mortar relentlessly until it was as smooth as glass to reduce hydraulic friction to the absolute minimum.
And here's where it gets really interesting. The Roman engineers deliberately built this internal channel 5 feet high, but they mathematically calculated the gradient and the flow rate so that the water volume usually only filled about 2/3 of the channel.
Yes, that's right.
The water is only ever about 3 feet deep. Why? Why expend the massive cost and labor to dig a taller tunnel, line the entire thing with expensive waterproof cement, and then intentionally leave the top 2 feet completely empty? It sounds like wasted engineering.
It wasn't wasted space, it was operational breathing room. That dark, damp, empty space above the rushing water line was absolutely essential for the human maintenance worker.
Like people went in there.
Oh, constantly. We have to dispel the myth that an aqueduct was a fire and forget machine. This system required constant, grueling human intervention to survive. Specialized workers, the aquarii, had to physically climb down through vertical inspection hatches spaced out along the route, drop into the channel, and walk for miles inside these dark, flowing tubes.
Imagine you are an Aquarius. That job sounds like an absolute nightmare. You're deep underground, crouching in pitch blackness, knee-deep in freezing, fast-moving water, trying not to slip. What are they actually doing down there?
They are engaged in a perpetual war against the silent chiller of any gravity-fed water system: friction. And the primary cause of that friction was the chemical deposition of calcium carbonate, commonly known as travertine.
Hard water deposit.
Exactly.
If you've ever looked inside your electric kettle or had to descale your coffee maker, you know exactly what this white, crusty calcium buildup looks like. Now imagine crawling through a pitch-black tunnel to chisel that out by hand.
It's unbelievable. The vast majority of Rome's best water sources were natural springs that percolated through limestone. The water was incredibly rich in dissolved minerals, making it very hard.
So it leaves a crust everywhere.
As this mineral-heavy water flowed continuously over decades, it constantly deposited microscopic layers of calcium carbonate on the interior walls and floor of the smooth conduit. Even a tiny millimeter-thick layer of this rough, crusty accretion completely destroyed the glassy polish of the waterproof mortar.
Does it really make that much of a difference?
Huge difference. Modern hydraulic research has shown that this slight roughening of the walls created immense drag on the moving water. It reduced the velocity so severely that it could cut the overall delivery volume of the aqueduct by up to 25%.
A 25% drop in a city's water supply just from microscopic mineral friction.
Yeah.
So these workers are walking miles underground, swinging iron chisels in the dark, meticulously hacking away layers of stone crust just to keep the water flowing fast enough to reach Rome.
Yes. They had to clear thick algal fouling near the vents, patch accidental leaks in the mortar, and painstakingly chip away the travertine without damaging the waterproof cement underneath. It was a delicate, miserable job.
I can't even imagine.
In fact, inside the actual city of Rome, where they utilized smaller lead pipes buried under the street curbs to distribute the water to neighborhoods, the calcium carbonate would build up so rapidly that it completely choked the narrow pipes.
And you can't climb inside a small pipe.
Exactly. You can't send a man with a chisel inside a 3-inch lead pipe, so the maintenance crews had to constantly rip up the cobblestone streets and replace the clogged mains pipework entirely.
Which brings up a fascinating point regarding the materials of Roman plumbing. We've talked about these massive stone conduits, but when it came to local distribution, the Romans used pipes made of ceramic, wood, and famously lead. Wood seems utterly insane for a pressurized water pipe.
It sounds deeply counterintuitive, but wood was surprisingly durable and cheap if deployed correctly. They heavily favored pine and alder wood.
Really? Pine?
Yeah, Pliny the Elder, the famous Roman author and naturalist, explicitly recommended these woods for plumbing. The trick is the environment. As long as the wood was kept completely and permanently submerged and buried in wet anaerobic soil where oxygen couldn't reach it, the bacteria that cause rot couldn't survive.
Oh, so it just doesn't rot.
Right. Archaeologists have actually excavated perfectly preserved wooden Roman pipes, tightly clamped with oak joints, at the Vindolanda military fort in Roman Britain and deep in the bogs of Germany.
Okay, wood makes sense if you bury it in the swamp. Ceramic makes sense because it's clean and doesn't taint the flavor. But lead.
Yes, the lead issue.
The Romans are historically infamous for their use of lead pipes to deliver drinking water. Greek and Roman physicians, like Celsus, absolutely knew that lead was highly toxic to the human body. They possessed clear clinical records of lead poisoning, causing neurological damage in silver miners and metalworkers.
They absolutely did.
So why on earth were the greatest engineers in antiquity piping their daily drinking water through a known neurotoxin? Did they just not connect the dots?
They completely connected the dots. Vitruvius wrote explicit warnings that water from earthen pipes was much healthier than water from lead pipes.
So why use it?
It was an unavoidable economic reality. It was a massive byproduct of their extensive silver mining operations in places like Spain. Consequently, it was incredibly cheap, plentiful, and unlike brittle ceramic, lead is highly malleable.
So it's just easy to bend around street corners.
Exactly. It can be easily rolled into sheets, folded, and soldered into complex shapes to navigate the twisting urban streets. But here is the truly fascinating, ironic twist of chemical fate. The very thing that choked their aqueducts, the calcium carbonate, is largely what saved the Roman population from mass, catastrophic lead poisoning.
The hard water crust acted as an internal shield.
Precisely. Because the aqueduct water was flowing constantly, 24 hours a day, it rarely sat stagnant in the pipes long enough to absorb massive, lethal doses of soluble lead.
Oh, that makes sense.
And incredibly quickly, that thick layer of calcium carbonate travertine would coat the inside of the new lead pipes. It essentially created a physical, mineral barrier, completely insulating the flowing drinking water from ever touching the toxic metal walls of the pipe.
Wow.
Now, it wasn't a perfect shield. Modern isotopic analysis of Roman skeletons and sediment cores from ancient harbors shows that lead levels in the Roman bloodstream were clearly measurable. They were about 100 times higher than the natural background levels found in local spring waters.
That's still pretty high.
It is. But because of the constant rapid flow and the heavy mineral crust, the exposure wasn't high enough to cause the acute systemic mass poisoning that modern pop history often claims brought down the empire.
It's an incredible paradox.
Yeah.
The internal friction that slows down the system and drives the maintenance crews insane is the exact same chemical process keeping the population alive.
History is funny like that.
Okay, so the water has survived the agonizingly flat gradient. It survived the explosive siphons. It's been insulated from the lead. And after 50 miles, it finally arrives at the edge of the sprawling city. What happens now? It doesn't just blast out of a tunnel into the open streets.
No, the journey culminates at a massive distribution terminal, a piece of monumental architecture, which the Romans called the Castellum Aquae, or water castle.
Water castle, I love that.
This was often a highly decorated, prominent building. Functionally, it acted primarily as a massive settling tank. The fast-moving water from the aqueduct channel would flow into these large, deep internal basins.
To slow it down.
Exactly. As the water entered the wide basin, its velocity dropped dramatically. This sudden slowing allowed any fine sand, gravel, or waterborne debris that had somehow made it this far to gently sink to the bottom of the tank where it could be swept out later.
Because nobody wants a mouthful of silt when they take a drink from a public fountain.
Exactly. The water has to be pristine. From the Castellum Aquae, the clean water was divided into different mains and sent out into the city. But the distribution was not egalitarian.
What do you mean?
The Romans operated on a very strict, legally defined priority cascade. The absolute highest priority, the untouchable tier of distribution, was the public basins and street corner drinking fountains.
Oh, so the public gets it first.
Yes. The provision of free, clean water for the general plebe in public was considered a fundamental right and a core expectation of the emperor's duty.
The public gets their water first no matter what. Who is second in the cascade?
Second in line were the massive public bathhouses. The baths were the absolute social, political, and cultural heartbeat of Roman daily life. They consumed millions of gallons of water daily, but bathers paid only a tiny, heavily subsidized nominal fee to enter.
And the third tier?
Finally, if there was sufficient pressure and volume left over, the remaining water could be sold to fee-paying private households. Wealthy patricians or profitable businesses would pay an exorbitant fee to the state treasury for the right to tap a private pipe directly into their villa or workshop.
And this private commercial distribution is where the history gets really mathematically weird.
Oh, yeah. This is wild.
They diverted the water from the castellum using standardized bronze pipes called a calyx. This pipe was fitted with a bronze stopcock to control the flow. There were 25 strictly standardized sizes of calyx.
Right.
If you paid a higher tax, you were legally issued a wider calyx. But as we discussed when digging through the research, the Romans, the masters of the geographic gradient, had a massive glaring blind spot in their understanding of fluid dynamics, didn't they?
It is arguably one of the most fascinating intellectual failures in ancient engineering, and we have a complete, detailed record of it thanks to Frontinus, who was appointed curator aquarum by the Emperor Nerva in 97 AD.
Right, Frontinus. He inherited a mess, didn't he?
Oh, a total mess. The citizens were complaining of severe water shortages, yet the springs outside the city were flowing at maximum capacity. Frontinus wrote an incredibly detailed, exhaustive official report, essentially a forensic audit of the entire imperial water system.
Right. He was trying to solve the mystery of the vanishing water. And in his audit, he discovers their core mathematical model is fundamentally flawed. Let me get this straight, because it blew my mind.
Okay.
These surveyors could calculate a drop of 17 meters over 50 miles to perfectly bypass a mountain range. But they couldn't figure out basic water pressure at the end of the line.
It seems baffling to a modern mind trained in basic physics, but yes,
Okay.
The Romans did not possess the mathematics of calculus, so they viewed water geometrically, not dynamically.
So what was the flaw?
Here is the exact fatal flaw. The Romans measured a private citizen's water allowance in a unit called a quinaria. The quinaria was strictly defined by the cross-sectional area, the physical size of the whole of the bronze calyx, where it attached to the wall of the castellum aquae.
So a wider pipe meant more quinaria, so you paid a higher annual fee.
Exactly. But they had absolutely no mathematical formula and no physical measuring device to account for variations in the velocity of the water or the pressure driving it.
Wait, let's break this down for the listener. If I am a Roman citizen and I pay the state for a 1-inch pipe, I pay the standard 1-inch fee.
Yes.
But if the city workers attach my 1-inch pipe near the top of the water tank where the water is shallow, the hydrostatic pressure is very low, the water just lazily trickles out of my pipe.
Yeah, you barely get anything.
But if my neighbor also buys a 1-inch pipe and he bribes a worker to attach it at the very bottom of a 20-foot deep settling tank, the massive weight of all that water above it is pushing down. His 1-inch pipe is going to blast water out like a modern fire hose.
It totally is.
He is receiving 10 times the actual volume of water I am. But because the physical hole in the bronze is exactly the same size as mine, he is paying the exact same tax.
You have just perfectly diagnosed the fatal flaw that broke the Roman water economy. They erroneously equated the static size of the hole with the total volume of water delivered, completely ignoring the dynamic speed at which the water was moving through that hole.
That is just, it's such a basic oversight.
It is, and this massive intellectual blind spot created an absolute free-for-all for municipal fraud and water theft. Because the state didn't track velocity, it was incredibly easy to manipulate the system and steal millions of gallons if you understood basic, practical plumbing.
And water was highly valuable, especially for commercial industries. Our sources detail the operations of fullers, the ancient clothes washers and dyers who required massive continuous amounts of fresh water for their vats. So how were people exploiting this flaw and stealing the water?
Frontinus became utterly obsessed with catching these thieves. His report reads like a manual on ancient utility fraud. Some people were simply illegally stretching or widening their lead pipes just past the official bronze stamp to secretly increase the flow.
Oh, just bending the metal a little.
Right. Some wealthy landowners would brazenly tap illicit pipes into the main aqueduct channel miles out in the countryside, siphoning off a massive private supply before it ever reached the city's castellum.
Wow.
But the most insidious problem was internal systemic corruption. People were bribing the aquaries, the state's own maintenance worker.
It was an inside job.
Completely. For a healthy bribe, an aquarist would gladly install a completely unlicensed pipe for your workshop or conveniently place your authorized calyx much deeper in the tank to guarantee you high pressure.
So Frontinus knew this was happening.
Frontinus realized with horror that the state was losing vast amounts of tax revenue and the public fountains were running dry. But because of his fundamentally flawed mathematical framework regarding velocity, he could never accurately mathematically quantify exactly how much water was being stolen. He just knew the system was hemorrhaging.
But if the imperial guards caught you stealing water, the penalties weren't a slap on the wrist.
Oh, no. The penalties were economically devastating. The Roman state did not tolerate tampering with its critical infrastructure. If you allowed a tree on your property to damage the conduit, the fine was 10,000 sesterces.
And if you messed with the water itself.
If you intentionally polluted the water inside a conduit, say, by letting your agricultural manure runoff seep into the channel, the fine was an astronomical 100,000 sesterces.
How much is that in context?
To put that staggering number in perspective, a common Roman legionary soldier earned about 900 sesterces for an entire year of brutal military service.
So you're looking at a fine equivalent to 100 years of a soldier's salary, just for muddying the water.
Exactly.
That shows exactly how vital, how existentially important this system was to the survival of the empire. Which leads us to the sheer mind-boggling scale of this gravity-powered machine at its absolute peak.
By the late 3rd century AD, the city of Rome alone was supplied by 11 distinct state-funded aqueducts. The combined length of these conduits stretching across the landscape was roughly 800 kilometers.
800 kilometers.
About 47 of those kilometers were carried high above ground on massive masonry arcades. The Aqua Claudia and the Anio Novus were considered the absolute pinnacles of this engineering, boasting the highest elevations and the most reliable flow.
How much water are we actually talking about per day?
Modern hydraulic estimates suggest that at its peak, this sprawling system was delivering anywhere from 520,000 to over 1 million cubic meters of fresh water into the city every single day.
To sustain a dense urban population of over 1 million people, it's an extravagant, luxurious water economy. But here is the thing that truly blew my mind in the research.
What's that?
I always thought of aqueducts as just municipal plumbing, getting drinking water to citizens.
Yeah.
But they harnessed the gravity power of these aqueducts for heavy, destructive industry.
They absolutely did. This is where the gentle gravity slope becomes a violent industrial tool. In heavily mined regions like Dolocothi in Wales and Las Medulas in Spain, the Romans constructed enormous temporary aqueduct networks purely for extracting gold.
Wait, how does water extract gold?
Well, they didn't build them with that gentle 1 in 4,800 flat gradient. They deliberately built them incredibly steep. At Dolocothi, the gradient was as sharp as 1 in 700.
So the water's moving incredibly fast, building up massive kinetic energy.
Yes, they would channel mountain rivers from miles away, racing the water down these steep artificial leats into massive holding reservoirs perched high above gold-bearing rock formations.
Okay, I think I see where this is going.
Down below in the mines, laborers would use the fire-setting technique to heat the rock face and weaken it. Then, at the precise moment, they would throw open the massive wooden sluice gates on the reservoir, releasing an entire lake's worth of water all at once.
A completely man-made, highly localized tsunami.
Exactly. The Roman term for this technique was ruina montium, the ruin of the mountains, though we often call it hushing. Millions of gallons of water would violently crash down the slope.
That must have been deafening.
The sheer hydraulic force would shatter the heat-weakened rock, instantly strip away tons of soil overburden, and wash the crushed gold ore down into heavily stepped channels where the heavy gold dust could be easily processed and collected. It was environmental devastation and hydraulic mining on a scale that wasn't replicated again until the California gold rush in the 1850s.
It wasn't just ripping apart mountains for gold. They used this exact same gravity power for the mass production of food.
Yes, industrial milling. The complex at Barbagal in Roman Gaul is the perfect example. An aqueduct fed a large reservoir, but the water didn't flow to a city. Instead, it was directed to pour down a steep 30-degree hillside.
Okay.
Built into this hillside was a cascaded series of 16 massive overshot water wheels. As the heavy water dropped from one wheel down to the next, the kinetic energy drove massive internal grindstones.
16 of them.
Yeah. This single facility milled enough flour to feed the entire surrounding region of Arles. They essentially took the passive concept of the aqueduct and built an ancient, gravity-powered, automated factory complex.
It is an indestructible, passive, gravity-fueled powerhouse of civilization. So, how does something like this fail?
Well,
How does a system made of solid rock, powered by the constant, unyielding pull of the Earth's gravity, actually come to an end? Does it naturally break down, or is it violently broken?
historically, it was a tragic combination of both. Targeted enemy action followed by the slow, suffocating decay of nature.
Okay, let's talk about the enemy action first.
The most dramatic, fatal blow to the Roman system came in 537 AD. The Western Roman Empire had already fallen, and the Ostrogoths laid siege to the city of Rome. The Gothic generals understood perfectly well that the city's lifeblood, its ability to withstand a siege, was its flowing water.
So they went after the water.
So they systematically located and physically smashed the aqueduct channels outside the city walls.
They just severed the arteries of the city.
Precisely. They cut the water, and they actually tried to use the dry, empty conduits as secret tunnels to sneak their troops past the massive city walls.
Oh, wow.
This forced the Byzantine defender of Rome, the great general Belisarius, to hastily block up the internal channels with solid stone masonry from the inside to stop the infiltration. But the real tragedy is that even after the siege eventually lifted and peace returned, the system never truly recovered.
Why couldn't they just fix them?
A few minor repairs were made, but the city's population had plummeted from 1 million to mere tens of thousands. The post-Roman authorities fundamentally lacked the centralized wealth, the engineering knowledge, and most importantly, the massive familia aquarum, the standing army of maintenance workers needed to maintain the vast network.
And without the workers, nature immediately takes the system back.
It always does. Think back to the travertine, the calcium carbonate, the silent killer. Without the aquarii constantly crawling through the dark with their iron chisels, the mineral accretions grew unchecked.
Right. The crust just kept growing.
In provincial areas, like the massive Eiffel Aqueduct in Germany, the calcium carbonate built up layer upon microscopic layer, year after year, century after century. Ultimately, it literally choked the channel to death.
It just closed up.
The conduit sealed itself completely solid, transforming from a water pipe into a solid vein of rock. The pressure built up, broken junctions leaked, and the ancient swamps and marshes returned to reclaim the land. The magnificent, towering stone arcades simply became ruined, baffling monuments in a medieval landscape.
So what does this all mean? The empire falls, the water stops flowing, the arches crumble into the riverbeds. How long did it take for humanity to relearn and replicate the scale of water transport?
It took roughly a millennium of dark ages. During the late medieval period, Rome's population was a shadow of its former glory, and the remaining citizens were back to relying on the polluted Tiber River, digging shallow wells, and desperately catching rainwater in cisterns.
Living exactly like their ancestors did before 312 BC.
Exactly. Only one ancient aqueduct, the Aqua Virgo, was still somewhat limping along, primarily because it was almost entirely underground and tapped a remarkably pure low-calcium spring.
So when did things change?
It wasn't until the dawn of the Renaissance in the mid-1400s that we see a true revival of large-scale hydraulics. Pope Nicholas V took on the massive civic project of fully renovating the Aqua Virgo in 1453, finally bringing reliable, large-scale flowing water back to the fountains of Rome.
It took that long.
And around this time, engineers across Europe began obsessively studying the towering ruins of the Pont du Gard and the Aqueduct of Segovia, slowly relearning the complex physics of the gradient that Vitruvius had laid out 1,500 years earlier.
It is an incredible journey.
Right.
I mean, think about the life of a single drop of water in this system. It bubbles up from an upland spring, perfectly captured by a stone basin. It glides down an invisible, mathematically perfect slope, tunneling through miles of solid mountain rock.
Yeah.
It plummets down into a canyon, surviving terrifying hydrostatic pressure inside a concrete-clamped lead siphon. It continuously insulates itself with a microscopic layer of calcium carbonate, fighting off tree roots and corrupt officials, until it finally emerges from a standardized bronze stopcock into the marble basin of a bustling, noisy Roman bathhouse.
Quite a trip.
It really makes you realize how incredibly fragile yet aggressive our modern systems are. I mean, the pressurized water coming from your kitchen tap right now is undeniably a miracle of engineering, but it is a noisy, active miracle.
Really?
It is deeply reliant on electrical grids, massive diesel turbines, and constant active energy input. The Romans achieved a similar miracle with pure geographic math and the silent, unyielding pull of gravity.
And if we connect this ancient history to the bigger picture of our modern world, this raises a deeply important question.
What's that?
Modern municipal water grids rely on massive, continuous amounts of electrical energy to violently pump water upward, forcing it against friction and geography to reach our high-rises.
Right.
Roman aqueducts ran completely passively, relying only on the Earth's natural contours. As we face escalating global energy challenges, and as we look for truly sustainable infrastructure that can last thousands of years, could the future of civic engineering actually look more like the ancient past?
Yeah.
Will we eventually be forced to design our cities to submit to the will of gravity rather than using brute electrical force to bend water to our cities?
That is a fascinating, profound thought to leave on. The invisible engine of the ancient world might just hold the blueprint for our sustainable future. Thank you all for joining us on this deep dive into the mastery of Roman water. Go turn on your tap, have a glass of water, appreciate the journey it took to get there, and we will catch you next time.